Okay, so let's start our lecture today. So, yeah. So last time we showed that this sigma is a well-defined function. So now we want to show that this sigma z is entire. So yeah. So let's erase some part. Okay. So the way that I want to show it is entire is that I want to use the property that so since I know that uh, yeah, I want to use the property that this sigma kz, right? Sigma kz is holomorphic. Shoot. So what do I want? So 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 basically I want to look at these functions, right? So because I know that this sigma kz is the limit of this function, and so aim to show that let's see whether we can show that this sigma k z is homomorphic on k. Okay, so yeah, because in this case I need to be a little bit careful. So about what do I mean by holomorphic on k, right? So basically holomorphic so holomorphic on k means that holomorphic on a neighborhood of k. Okay, so I think I want to use a like the because I know that the local uniform limit of a holomorphic function is holomorphic, right? But I want to be more detailed because I think there is some ambiguity between the version that's ambiguity in my mind about the version of the version I learned in class and also the version that I want to use here. So yeah, let me try to find the version that's I'm trying to look at. So this is not here. Okay, from a line ago. Identity theorem. No, open mapping theorem. No. So value theorem, algebra. Okay, so here we go. So Okay. Oh. Shoot. Okay. So. So. Yeah. So I know that I know that this function is okay. So okay. So I know that uh, L of n naught n naught upper n z is well defined on K, right? However, outside of K, yeah. So the question is that, is it still defined outside of K? Let's think. So for any z's outside the K, I think that still depends on like the because yeah, I think it's still defined on over like a neighborhood around K. Okay. And also a neighborhood of K. So maybe let me add. So yeah, so because this n basically is bigger than this n naught plus 1, or bigger than or equal to this n naught plus 1. So the reason for that is I think for this omega j, right? So for this omega j, we know that for this n large, the modulus of omega j is bigger than 2r, right? So that so that this z over omega j is less than equal to modulus of z over 2r, right? And we know that modulus z is less than r, so the whole thing is less than 1/2, right? It's less than 1/2. So for n bigger than n naught plus 1, so this guy z over, and also z in k, okay. So we have z over modulus of omega j is less than equal to, oops, I think it's the modulus of z over omega j is less than equal to r over 2r, right? Which is equal to 1/2. Okay, I think it's strictly less than. Okay. And then, so this implies what? So this implies that so when this z is slightly larger, right? The ratio is still small, but maybe it's some ratio that's bigger than 1/2, right? But still, it is less than 1. So let's see. So for z to be in the closed disk of radius let's say 1.5r, which is 3 over 2r. So we have z over modulus of z over omega j is less than 3 over 2r over 2r, so which is equal to you multiply by 2 on both sides, and then you have 3 over 4r, 3 over 4. Okay. So this implies that we have 1 over z over omega j is still lies in because here we have 1, right? And then it is it can be at most 3 over 4, so it still lies in the disk center at 0 of radius 1. Okay. Shoot. Okay, so what I'm thinking. So radius this center 1 of radius 3 over 4. Okay. Okay. Yeah, because we do have the strict equality, because we know that the modulus of omega j is strictly bigger than 2r. Okay. So yeah, so we do have that, so that this log function is well defined, right? So this implies that yeah, so this implies that this L n naught n z is well defined on this disk. Okay, like an enlarged disk. Okay. So let's see. So here, what do you want to show? Okay, I don't think I even need the closure. Okay, I don't think I need the closure. I think I just need the open disk. Okay. Because I want to use the theorem that's a sequence. If let's say you have a sequence of holomorphic function being defined in an open set, and then this sequence of holomorphic function converges on any compact subset of this open set to an entire function. Oh, sorry, not to an entire function, to a function that's to a limit function on this open set. And then this theorem just says that the limit function is holomorphic. Okay. So let's say so here I want to show that so this sequence of function, okay. So this sequence of function is actually holomorphic. On this open set, right? So basically our goal is to show that okay, so our goal is to show that okay, so here because eventually this is being taken exponential, right? So because the combination of holomorphic function is also holomorphic, so therefore if I show that this LZ, the LNZ, right, which is the limit of this guy, oops, the Ln not Z, okay. If I show that the Ln not Z is holomorphic, okay, then I think I'm done. I think I just because if this Ln not Z is like holomorphic, then this guy is also this guy is holomorphic for sure, right? Because it is just because there is only finite many functions, right? Many product. Each product is a holomorphic function, and the product of holomorphic function is the product of holomorphic function. So I know that the combination of holomorphic is holomorphic. So the product of holomorphic function. Okay, so that's the product of the holomorphic function. Okay, so I think it is okay, so let's set that for a while. Okay, so let's focus on first showing that. So our goal is to show that. Okay, so goal, let's say let okay, so that let's say K prime, okay, so oops, be a subset of this disk, right? Oh, actually, wait. Actually, I think there's a better way to do this. So, yeah, so instead of enlarging the radius of this R, right? Yeah. So, okay, so I think maybe let's just do this. Okay. So fix any compact set. Right. So yeah. So